Okay, so let us see how you go about this question. Still is motion under gravity. It says a particle is projected vertically down upwards, and at the same instant another is left to fall to meet it. So what we are having, we have a particle which is the first particle is projected upwards like this. So it is going there. Then another one is left to fall. So if it's left to fall, it's coming that way. This is going to be the second particle. Second particle. And this one is going to be our first particle. First particle. Now, because this one is just being, because not that this second particle is left to fall. So if you are holding someone and leave it to fall, for example, if you can see this chalk here. If you can see this chalk here, if I leave it fall, it's that it's having at the first step, it's having zero velocity. So when I leave it fall, it's that it's starting from zero, then I leave it fall. So meaning at this instant here, there the initial velocity here is zero. Our initial velocity here is 0 meters per second. This one is projected, so we don't know the velocity at which it started because it's projected upward. So meaning it has a certain velocity. Now, from there we are seeing also there. So from here, I can straight away get my initial, because this one is falling downwards, the acceleration, remember it's going to be accelerated by gravity. That's why we say it's being accelerated by acceleration of the gravity due to gravity. It's accelerating due to gravity. So the acceleration there is going to be positive there. Now this one, because this one is going upwards there, it means that first of all, its acceleration is going to be negative d because it's opposing gravity. So that's what we have at first. Now, because they are being released at the same time, it means that they are going to meet when they are used the same time. Because this one is released and this one is projected upwards. So the time they are going to glide, if they are gliding here, this one now use the same time, and this one now use the same time. These are the things I'm putting here. The first, since the particle have the same speed, so they are having the same speed, meaning they are going to glide, the final velocity here is going to be the same for this and this. So now here, from here, for the first particle, for the second particle, can we use this first particle? Okay. Let me start with the first particle here. Our first particle. Its displacement, okay, ut plus a half at t squared. So let me call it displacement 1. It's going to be our u, we don't know that u. Let me call it just u. Then our t, let me call it t. Then minus a half, because this e is negative t squared. There. Now if I come here on the second particle, here, first of all, its s is going to be now u into t, because they are having the same time, not collision, because they are being released at the same time. A half dt squared. So here, time they will use before collision is the same. So now, here, by telling us that from here, you can see this one is starting at 0. Now, if I want to get the final velocity of this first one, v is equal to u plus 8t. So our v is going to be equal to, this is 0, plus, for the first particle, for the second particle, then our acceleration is t. So our v here is going to be t. What about the final velocity for this? Now, for it, you see, there you have our v equal to u plus 8t. So here our v is going to be u. Our u is what? Here it has the u, which we don't know. Then minus a, which is negative v, then t. But now note from here, we say they are going to be having the same velocity. So if this one is 1, okay, let me call it 2, and this one is 1. We say, because they are moving at the same speed, so meaning the final velocity of collision is going to be the same. They are moving at the same, this one, because what they are telling us that they are moving at the same speed. So this one is falling at the same speed, and this one is coming at the same speed. So when they ride this, their final velocity is going to be the same. So meaning that now, From there, is that R1 is going to be equal to 2. So from there, U minus dt equaling to dt. Don't be confused. These ones don't cancel. What you do, you take this one instead and you see we have it equaling to dt. So now I want to make the time, because the time they are using the same time. So from there, so our t is going to be u over 2g. Now if I have this time, now I can show that they want to show that if the particles have the same speed when they glide, one of them has traveled 3 times or twice the distance traveled by the other. So what we do is that this one, I can come and from here, for the second particle, my S2 is going to be ut plus a half dt squared. But this one now, remember our u here is 0. dt squared, so our S2 now is going to be a half dt squared. Now, we have here our t for the second particle. So for our first particle, we have its c is here, and then for the second particle, we have its sets there. So our S2 here is going to be a half d into now our t, which is u over 2g, the whole square. So if you simplify this, you see that we have, this is going to be a half g, then this will be u squared over 4g squared. Why? When you square this, you get this. When you square 2, you get 4. When you square 2, you get this squared. So our S2 here is going to be u squared over, this one is going to cancel this one, I have 8g. When I cancel, what about this one? From here, our S here, is that our S1 here is going to be ut minus a half gt squared. Now, from there, can you substitute some chalk? Okay, now, we start now here. What I'm going to do, now I'm given t. So we have this t, we have also that t there. So can we substitute now? We are going to be having now our s equaling to u into u over 2g, then minus a half g into u over 2g, the whole square. So this will give us s1 will be u squared over 2g, then minus a half g into u squared over 4g squared, which is squared is there. So what happens there? You see, we are going to be having our S1 as u squared over 2g minus, when I open brackets, this will cancel, so I'll be having u squared over, I'll be having now 1 will cancel, this g will go with 1, like this one did. So I'll be having now 8g. So now there, and to simplify, we can get the LCM, which will be the same as our LCM here is 8g. So this one goes here 4 times. So this will be 4 u squared, then minus this goes here, u squared. So it's that our S1 is going to be 3 u squared over 8g. Now, which you can easily see, my S1 is going to be, okay, S1 is going to be, if I factorize out 3, I'll be having u squared over 8g. But what is this? So this one is our S2. All this is our S2. So our S1 here will be equal to 3S2. So you see that the proof will be that now. This one here, you see that is it there. It's going to be our S2. So now what shows, because I told us has traveled thrice the distance. So it's that the distance of the first particle is 3 times the distance traveled by the second particle. And so our proof is done there. So that's it, members. We are going to see more proofs using these motions under gravity. See you there. But please don't forget to subscribe to the channel.